tell you that. अभी नहीं, हाँ? तो मतलब वहाँ जाएंगे ना जी, तो मैं सिग्नल दिखाता हूँ.
So where all it goes live?
YouTube location.
Okay.
Recording. Yeah.
This only the slide goes.
Yeah.
Okay.
Yeah. But is it a Jyotishman?
It's okay.
Huh? But if you don't want, we don't have.
He's an
Oh, everything mine is out there. So that's how I.
Good afternoon, everyone. Let's start the colloquium today. Our speaker today is Roxy Mathew Koll from Indian Institute of Tropical Meteorology, Pune. Roxy is hosted by Arnab and Sandhya. And I'll ask Arnab to introduce Roxy before we start the talk. Arnav.
Okay. Welcome to TIFR. It's a pleasure to have you here. So Roxy Mathew Koll, a scientist at the Indian Institute of Tropical Meteorology. Uh, I think we should have such sessions which are a little bit interdisciplinary, combine all the fields that we work in, which are all linked to basic sciences. And so Roxy is, of course, a very well-known climate scientist of India. His main thing is on the interaction of the atmosphere and the ocean. And I hope after the talk, we'll be able to go outside and see the interaction of the atmosphere and the ocean. He has been on the IPCC panel for climate change. He leads the Indian Ocean Regional Group or something of that sort. And he started off in QSAT, and then from there, from Kerala to Hokkaido University, PhD there, postdoc in Italy, and then came back to the Pune. And why am I the host of, or Sandhya the host of somebody in climate change, right? It's what you must be wondering. So Sandhya and I have been working together for a while on interesting topics. And we decided that we should do something, these topics which, so we got a student from TIFR, Harsha is here, and she's trying to figure out what kids know, actually what kids don't know mostly about climate change. And so when we were, discussing this, I said, I think we should do this. I've been reading this thing. So it turns out that we were both following the same person, and Roxy, Roxy, is also at Roxy, Rockksea, Roxy. Okay. So he's Roxy on Twitter and other, social
Thanks
media.
for advertising me.
Yeah. And I mean, he posts some very, very insightful things about climate change, especially in the Indian context, because most of the, I don't need to know more about the Keeling curve and some measurements in Hawaii. I need to know what's happening here. So we landed up that, okay, let's get him to TIFR. And we wrote to the then colloquium coordinator, JD. I don't know if he's around. And Roxy, of course, was very kind enough to say yes. But then, he got the Rashtriya Vigyan Puraskar Yuva.
Used to be Bhatnagar.
The Bhatnagar, basically. New version of Bhatnagar. And then things got delayed. The baton passed on to Manoj. But we are delighted that you're here today. Thank you so much. And I'm sure we're all interested in learning about monsoons, climate change, and all that from the experts. So over to you.
Thanks a lot, Arnab. I have the mic and we can keep it for the audience.
Papers and other places. And there's a compilation of what he writes on his website. And especially for the younger people in the room, it's immensely useful to sort of look through those. Very accessible and non-alarmist.
Okay, apparently the mic wasn't on, but anyway.
Yeah. Well, thanks a lot, Arnab, Sandhya and Manoj and TFR community. It's actually a delight to be here, actually. I never thought you had such a beautiful campus over here. After the invite, I first checked where it is actually in Mumbai, and I found, okay, it's bang on the sea. And once I came here, even in Google Maps, it looks so beautiful. And once I came here, it's so beautiful.
The question is, will it remain beautiful, or do you think we're going to be...
Exactly, that's what we are going to talk about. Whether see, my title itself is Warming Waters, Shifting Winds and so on. So I already heard, stories from Arnab where roof of his temporary lab has been thrown away with these kind of winds that you saw over the Arabian Sea. So I work at IITM, Indian Institute of Tropical Meteorology. It's under the Ministry of Earth Sciences. We have like 7-8 institutions under the ministry. One looking at totally on the ocean. One looking at IMD is also under the Ministry of Earth Sciences. So at IITM, we have... I forgot about it. Otherwise, I would have stuck at the first slide. Thank you. So we have about 150 to 200 scientists working mostly on the monsoon itself. Some people are monitoring the monsoon, trying to understand the monsoon using radars, using observational setups. Some people fly the plane and see if they can make monsoon rains. Some people try to read the monsoon signals from, paleoclimate proxies like tree rings, speleotherms, corals, and so on. And some people, there is a big modeling group trying to understand the changes and also see how we can predict the monsoon in the next few days to season, and also how we can project the climate for the next several decades so that we can prepare ourselves for it. So in part of this journey, we have got an understanding on how the environment around us is changing in response to climate change, global warming, and so on, how it is affecting locally in India, how the monsoon, the lifeline for many of us. I will show why it is a lifeline as well, and how many other weather events are changing, and how we try to quantify it, so that because if we measure it, we can know how to manage it or how to prepare for it. Because if you don't know difference between 10 millimeter rainfall or 100 millimeter rainfall or a 3 millimeter sea level rise, what does 3 millimeter sea level rise corresponds to you over here? You just asked whether TFR will remain. Yeah, actually there was I remember a few years ago, there was news reports saying, okay, Mumbai will get submerged by 2050 or so on. Yeah? Yeah, don't come to Pune, okay? We are already, there's too much of urbanization happening. We used to think earlier when I was in Pune, we used to think, okay, everyone is going to Mumbai, so it's still pensioners' paradise. But now Pune is just coming up like Mumbai, and it's merging kind of. So anyway. And many of the impacts that you get affected here kind of reach Pune also over there. And here we have a small cartoon comics. I just want to, she's a survey person. I want to do survey. Who all has read Calvin and Hobbes? Just raise your hands. Others have not read Calvin and Hobbes, the comics. Okay. Yeah. So I think 60%, I feel. So 40% do not know Calvin and Hobbes. Or maybe they are not raising their hands. That will count as 10. Yeah. Perfect. That's beautiful. No, the reason why I say is that I went to a university and presented the same comic, and maybe 5% raised their hands. So I was like ashamed, and I was like in some old era, and nothing against you guys, okay? So, but this comic kind of briefs what is happening with climate change. People know parts of it. They ask questions. This is also part of your survey, Sandhya. Mom, what is that I hear about this greenhouse effect? And he has some idea, okay, there are some pollutants, is air pollutants and emissions same. So something is, we are emitting something, and that is, melting ice caps. And the third is very important because he says you will be gone by the time it happens. Yeah, and this is something I want to emphasize on, because most of the times, by the time impact is there, we will be there also, and it's not his generation or her generation, but for generations to come. And the last one is what we are doing about it. Whether we are doing anything about it, we still want to be chauffeured around. We are not doing anything about it. So monsoon, the winds are a key theme of today's talk. I will explain this chart. You might have seen these kind of charts, but this is a snapshot of one day of the winds across the globe, and one day from the monsoon time. I think it's June or July, something like that. And you would see I have put some arrows. We have the Pacific Ocean here, Indian Ocean here. Yeah. I can use the laser pointer. Yeah, we have the Pacific Ocean here. We have the Atlantic Ocean here and the Indian Ocean here. The Pacific, it's open to the north and south. Atlantic open to the north and south, but this is landlocked. We have India over here, and that changes these winds. Now, these winds, what are these winds? These winds which flow towards the equator, they are called the trade winds. So you have maximum energy in the tropics, and because of the Earth's rotation, they flow in a particular direction. And winds. So these trade winds blow from east to west, and they are generally called by those names easterlies based on the direction from which they are flowing. So east to west, easterlies. So easterly trade winds mostly, and here also easterly trade winds. But here it is totally different. So what happens is, and this is a picture from summer, northern summer, that is when June, July, or August, when the northern hemisphere has the maximum solar insolation, when we get the sunlight maximum. So the northern hemisphere, including the land, heats up maximum, right? So there is a temperature gradient. And land heats up much more during the northern summer, for example, in the northern hemisphere. So this land is much more hotter compared to this ocean here. So that makes a temperature gradient and a pressure gradient also. So there will be a low pressure here and a high pressure here. So that makes these trade winds in the southern hemisphere. These are actually trade winds in the southern hemisphere, just like this. They cross the equator and blow to the Indian subcontinent. So what we are actually getting as monsoon winds are actually easterly trade winds in the southern hemisphere, crossing the equator and reaching India. And we call them, because for India, they are coming from the southwest, we call them southwesterly trade winds, or southwesterly monsoon winds, or summer monsoon winds. Now, I told you about temperature, land warming, ocean conditions, and all this. Now, with global warming, all these are also warming, but unevenly. They are not warming evenly. So that makes changes in these gradients as well, temperature gradients. So some parts are warming more than the others. So that changes the monsoon winds. And if monsoon winds changes, you can see how it blows all the way from South Indian Ocean to North Arabian Sea, and then towards India. Part of it goes to Bay of Bengal. It also curves back to India. So all this moisture is coming from the Indian Ocean. So if any of your questions in between, please be happy to raise your hands and ask. Africa should have been hot in the sense. I have not shown colors here.
Why did it turn towards India and not towards
So the topography also matters. Topography matters, and the rotation of Earth also matters. So in the northern hemisphere, the currents, the fluids are, because of the rotation of Earth, they tend to turn to the right. And yeah, so due to the configuration of the continents and the rotation of Earth, so because of that, you get a turn like that. Yeah. So all these are changing. Differential heating happens. And during winter, it's the other way, because winter, the northern hemisphere is not as warm as summer period. Yeah, it is relatively cooler, and the oceans or the southern hemisphere is much more warm, so the winds blow the other way. But it's not blowing from the ocean side. It's mostly blowing over the land, and you don't get that much rains as the summer or the southwesterly monsoon. Now, because it comes from this direction, we call it the northeast monsoon. It's coming from northeast. This is a interesting picture on how life survives on many of these monsoon winds. So this cuckoo was tagged. It's a Mongolian cuckoo, and it was tagged from somewhere north, in the Mongolian region of China, and it was tracked over, I think, around 2 or 3 years. It's a famous Mongolian cuckoo, and it was tracked. And depending on the season, it took different tracks, but also it had a dependency on the monsoon as well. You will see from the next one. So this is in 25th September, when the monsoon winds is end of September. Monsoon is kind of weakening. The summer monsoon is weakening. So the winds over the north are kind of more favorable for the cuckoo to travel. So why does this? It goes back and forth between Africa and Mongolia through India. So you can see the track it took here. It's kind of following the winds, where the winds were strong, so that it can stay aloft over the sea for quite a long time. And travels like several thousands of kilometers across the sea, non-stop. This is in May, just before the summer monsoon starts off, but still some prevailing winds were there. Yeah.
How long did it take for it to cross from India to Africa?
India to Africa. So just the entire track, if you disregard the stops, maybe 2 weeks. Yeah. But it stops in at some locations, like in Arabian Peninsula. Sometimes it stops and then goes. So if you take only the flight, 2 weeks, and it crosses this in a couple of days. Not this one, but this over the sea. No, it has stops in between. It has stops in between. So it stops in multiple places on its track. Over the sea,
Yeah.
like this over the sea, just 2 days. Yeah, so I'll show you another one, for example. Yeah. So this, I don't know how many days it took, maybe 5 days or 4 or 5 days. And this is without a stop over the sea. And if you fly in May, you will get the early rains by end of May. So they stop over India for quite some time, and then they continue again to Mongolia. So this is the time when a lot of life sprouts out over India with the early rains. They feed on all the life, from small caterpillars to worms to insects to smaller birds and all, and then move on to Mongolia. So they follow the track of the monsoon often. And this is coming back, and we lost a signal at somewhere in Yemen. So you can see Onan leaves India. So it left India and reaches Yemen. This was one flight, 3,500 kilometers without stopping, 68 hours. Yeah.
That's not even me. Just because this is not the most impressive, like there is
Definitely.
the bar tail godwit with 16,000 kilometers in 12 days without coming down or stopping it from Australia to Alaska.
Right. Anyway, so that is just one thing. Just giving a sample of how life depends on the monsoon and so on. This shows phytoplankton blooms. So whatever you see, like slight shades in that, that blue, including the green colors, are blooms of phytoplankton, the microscopic plants in the ocean. So if you take a, breath of air and out, yeah, thank you. Yeah, I sometimes try to do that with my audience. So about up to half of that the oxygen in that air were produced by this phytoplankton, but millions of years ago. So there have been all these pseudoscience. Okay, if you plant some trees, you get suddenly some oxygen and all. That doesn't work. It doesn't work that way. Yeah. So same with carbon sinks also. They will not suddenly absorb all the carbon emissions if you plant some trees and all. That will kind of regulate your microclimate. If you have trees around, definitely microclimate, but it doesn't connect largely to the unless you have something like entire Western Ghats forest or Amazon forest, which kind of can regulate large-scale climate system. A few trees will not, add to climate mitigation in a large way. Definitely, it will hurt, but so that will hurt. I'll show you. I have a slide on how it hurts. So, for example, if you have heavy rains falling on a barren land, the impact will be much more, especially if there are hills and all. Potential for landslides are higher. That's just one example. So this example of that phytoplankton blooms in a closer way on the beach, and this is the primary source of life, which connects to the zooplankton in the sea, which connects to the fishes, which connects to the humans over here. And there is another way by which these monsoon are manifested. You can see the same winds that I showed earlier are kind of associated with the clouds, the movement of clouds also. It's carrying all that moisture from all over the ocean and bringing into mainland India. And you can see this is the rains mapped here. So even though we have all these clouds and winds and all, it will rain in over some locations based on the amount of moisture and also the topography, the orography of that region. So suppose you have Western Ghats, it helps in lifting those moisture-laden winds. It goes up, condenses, and follows rains. So that's a beautiful way of how the land surface processes are important for bringing those rains locally. So you just by living on the coast, you will not get rains. If you have some more hills, Western Ghats, like we have on the west coast, you will get much more better rains. And you might get heavy rains and extreme rains as well, because orography can amplify and keep that moisture inland. Just like the Himalayas are kind of keeping that monsoon rains within India. We'll see that as well. Now, this is a much more larger picture. And here, we have the difference between summer and winter. And you can see the colors and differentiate the summer and winter. And the red colors you see in summer is located north. You can see the Indo-Tibetan Plateau, some part is actually white. This is actually beyond the 30 degrees Celsius, which means that area, Indian subcontinent and north of it, gets much warmer. So that's what drives the monsoon winds. So if you look at the rest in summer, you don't see such a north-south contrast, right? You don't see such north-south contrast here, but the north-south contrast is much more higher over here when we compare winter and summer.
Surface temperature, are you measuring the temperature on the ground?
So here, this is near surface temperature, a temperature at 2 meter height or somewhere in between.
Wet bulb temperature or the dry bulb?
Not wet bulb, just yeah. So, and here you can see the difference in a much more acute way. These are the difference between summer and winter temperatures, what I showed earlier. So here I showed the summer and winter temperatures. Now this is the difference. You can see it goes up to 30-40 degrees Celsius in that Tibetan Plateau. This is much more zoomed in version. While the range of change in temperature, between summer and winter, that's what I'm saying. This is not climate change that I'm talking about, between summer and winter. Over the ocean is around 3 to 5 degrees Celsius. So that temperature difference make a huge gradient to pull that monsoon onto the land. This is a kind of animation. So this is the only video. So when I came here, I was asked whether there are videos and all. I don't have much videos. Most are static images. Rest of the animation I try to create myself. So You can see by July, August, it's progressing north. The winds are strengthening. And this is the kind of monthly annual cycle of rainfall that we get over land. So again, winter, it's disappearing. We have the northeasterly winds and so on. Let me see. Yeah. Now, this part, maybe some of you have heard about it, the history of monsoon as well. So if you go like 70 million years ago, Indian subcontinent was again in the southern hemisphere. And we have remnants of that even now. So if you take some, I think basaltic rocks and all, I'm not a big time geologist, but the direction of the I forgot, but you can based on the location of the magnetic pole during those 70 million years ago, the nodules or whatever it is in there are aligned in a particular way. So you can take a rock and date it back to where it was formed. So some of the rocks in Maharashtra, they were formed in when India was in 20 degrees south in the southern hemisphere. Yeah, that's another set. Yeah. So so we were all part of, we were all together, Antarctica, India, and everyone. Then at some point, India started moving north at about 15 centimeter per year. That is a very fast motion. And one reason could be because India was kind of volcanic in nature. The crust was full of lava motion and all, which made it maybe slide much more faster. And then it moved about, collided with Asia 20, 30 million years ago. And bam, we had the Himalayas, which kind of made that temperature contrast, pressure gradient for the monsoon to flow. But at the same time, about this 70 million years ago, we had totally different kind of life over India. This is Rajasaurus narmadensis. Remains are found in by the banks of Narmada and all. That's why. So we were talking about Indore and all. There they have the some of the fossils of some of these dinosaurs. And because of that volcanic eruption, this is called Deccan volcanism. This is one of the theories postulated for the mass extinction. So there is one theory of the asteroid hitting and all, and maybe connected to the multiple asteroids hitting. There were a lot of volcanic eruptions at one time, which resulted in change in climate as well, change in all these conditions, which resulted in the demise of these dinosaurs. This is a remnants of Deccan volcanism. If you travel around Maharashtra, Mahabaleshwar, you can see these kind of hills. These are layers and layers of lava deposited over millions of years. That's why you can still see these kind of layers. Now, coming to climate change, one of the questions that I get very often is, hasn't the climate been changing for over a long time? Aren't there natural cycles of climate? So this is one factor that we talk about when asked these questions. Of course, there are these natural cycles, but according to these natural cycles of Earth or the solar system, we should have been actually having cooler temperatures, because this is something that we can precisely measure, and its contribution also can be precisely measured. Its effect on Earth's temperature and the climate system can be precisely measured. And let's see how it, yeah. So you can see the movements. You might know this already. You have the orbital cycle, which changes over 100,000 year cycle. The wobbling, which changes over 26,000 year cycle. And the tilt of Earth back and forth, which changes over 41,000 year cycle. Now, this doesn't go parallel all the time. They might be in phase or out of phase. So depending on that, it could be anywhere between 20 to 40,000 cycle of climate. And based on this cycle, actually, we are not in the very warm phase. It should have been slightly cooling actually during this time. Which is why, and also satellite observations show that over the last 40 years, the solar radiation has actually decreased, but still the temperatures are increasing, which means something else is increasing that, which is why we reach to these carbon emissions and greenhouse gases. So there are multiple ways: generating electricity, transportation, industry, agriculture also, commercial ways, residential ways. In multiple ways, we burn the fossil fuels. It could be in solid format in coal, liquid format as in petroleum or gas. And this results in carbon dioxide emissions, methane, nitrous oxide, and other gases. And that kind of trap the heat. So these greenhouse gases have a different vibration, especially when it is kind of transparent to shortwave radiation or the sun's radiation. But when the Earth emits the heat back as infrared or long-wave radiation, these molecules, greenhouse gas molecules like carbon dioxide, they vibrate in a high frequency such that it traps that heat within the system itself. So it sends back, or it keeps that within the system. That's how it warms the Earth's atmosphere, which is around maybe 10, 12, especially the troposphere, within which most of the gases are present. Now, I thought I had a slide on the potential. I think I'll get there. So when we have more heat trapped, generally, so the warming happens over the surface and then goes up. So that makes it much more unstable. So there is much more warm and less dense air. So there is more moisture also because the oceans are warming. So warm moisture means it's lighter than dry, cold air, which is denser. So if you have warm moisture, it will arise, it will ascend to the top of the atmosphere. That's a kind of unstable condition, which results in convective processes. So if there is moisture, it will make clouds or sometimes cyclones over the warmer seas and so on. So that's a basic process. And there is a relationship also if, for example, in the tropics and all, if there is a 1 degree Celsius rise in temperature, and if there is sufficient moisture, it can result in 7% increase in rainfall or convective activity. And if there is monsoon-like conditions, it can go up to 10% because the winds are also working along with. So there is a thermodynamic response where, okay, you have increased moisture, increased unstable conditions directly due to increasing temperature, but also the dynamic influence also. Now, this is a simple way of envisioning that climate change. So we talked about Milankovitch cycles, but climate generally, if you take few 100 years, that also has variability, year-to-year variability as well as decade-to-decade variability on how the internal systems work and all. So you can see this is how generally that climate variability is. Or if you stretch it for several millions of years, we will see the Milankovitch cycles as well. But when we add an external forcing, where, for example, carbon dioxide increasing monotonically, it will result in a system like this, where we have variability, but it's on a slope. So you might still have winters, for example, but the winters will be warmer than earlier. You might have El Ninos and La Ninas, but the El Ninos will be much more warmer, and the La Ninas will also be much more warmer than earlier. So that is the kind of slope we are in. And through paleo measurements, paleoclimate measurements, and many other measurements, and also modeling, we can study the past climate. For example, if you drill 1 meter in the Arctic or Antarctic, you might get a core which has preserved this again layers of ice over thousands of years, and it has the air bubbles trapped in there, which has a chemical composition of carbon dioxide from that time. And you can understand the composition of air in that time and also quantify it. So we can see that, okay, over time, the carbon dioxide levels have remained same for, for human scale, but it has pumped up to higher concentration in the recent period, and correspondingly, the temperatures have also gone up. So this 1.1 degrees Celsius is the change from the average global surface temperature. Anybody know what is the global average temperature, surface temperature? It's around 15, 16 degrees Celsius, okay? So when we talk about 1.5 or 2 degrees Celsius at IPCC level or UN level, or globally, we try to contain that. It is that departure or increase from that global mean temperatures that we have measured over time. Yeah. Huh.
No, next today. Today.
Yeah, just a second. Think. Sorry. No. Huh.
Back of how the temperatures will go down. Why is that?
So for the temperatures, there is always the interannual, decadal variability, and so on. So yeah. So there are, for example, I would say volcanic eruptions, which have a strong impact on the climate. Yeah. So I don't remember exactly this many years back what happened, but many of the dips corresponds to major volcanic eruptions, dipping the temperatures for a few years, maybe 5 years or 10 years or so. And you can see that correspondence as well. Also, the climate system goes through different phases of variability. And you see that represented in there. But if you look at the trends, long-term trends, so I see that there is some dipping as well. So this dip might be due to, I don't know exactly what it could be. Yeah.
So what is the shaded area? Is it the error band or something?
Yeah.
Uncertainty band?
Yeah, that's the uncertainty band. Yeah.
When you estimate atmospheric carbon dioxide levels by drilling into ice and looking at the trapped one, won't that be modified by the diffusion of gases through ice? Is that a significant thing?
Oh, I don't know. I haven't done, I don't know how much of modeling also goes into that kind of analysis. I think the longest records have been from the Vostok ice core from Russia. Goes to 800,000 years or 80,000 years. Yeah. But I don't know how much of a diffusion, because it's much deeper, and these are air bubbles trapped. Beyond that, chances of getting diffused, I think. I do not have a clear understanding on that. Beyond that, yeah.
You say 80,000 years.
Huh.
Ice ages.
Yeah.
Around 1,000.
Huh. Yeah.
They're supposed to be made from an ice age.
Mm-hmm.
So is that
I don't know exactly. Yeah, I can't say that right now. Yeah. But anyway, remember I told earlier that, okay, for the last 50 plus years, solar radiation has actually reduced slightly. I don't know if that has any connection with that slow. Yeah. Surface temperature, yeah, over the whole globe, including land, ocean, everywhere. And land is warming much more than the ocean.
coverage of the whole sphere, right? You're probably taking data.
Yeah,
And then
definitely.
use a model to interpolate.
Model to interpolate.
Is
Yeah.
This temperature, like,
Huh.
is it the geometric average on the surface of the earth? Is that how I'm supposed to interpret the 16 degree that said, or is it the average of every place you have covered?
It will be the so based on the average, we fill up the data also for the missing places with the model, and then so it's the average for the entire globe. That's how we take.
The missing places are mainly over the oceans, right?
It depends on the time. For example, yeah. So if you go before 1940s and all, definitely missing place over the ocean a lot. Yeah, all remote places. Yeah, pretty much. And since 1980, so even before 1980s, most of the ocean data used to come from voluntary ship observations, which were scattered over the shipping routes. Yeah. And for example, in the Indian Ocean, the first one expedition happened between 1950 to 55. And before that, it was like unknown. There were not much observations in the Indian Ocean even. But we have, for example, last since satellite era, now it is 45. I mean, since we started getting high resolution data around 1979-80, so we have 45 years of need data for the last 50 years. But if you look at India and all, the IMD has been observing station-based data from 1870s onwards. Actually, they have a station from 1850. And we have daily data, rainfall data, gridded data for across India. And this is something anyone can use actually, from 1900, 1900. That is like almost, how many? 125 plus years of daily data. So there are, of course, a lot of averaging, a lot of modeling as well, based on our both data and physical understanding. But now the key thing here is, this is again with Calvin I'm showing, the key thing here is the lifespan of carbon dioxide. So carbon dioxide stays in the atmosphere. So once you emit, even if you stop all these lights, our cars, industries, everything, it still will remain in that air for the next hundreds to thousands of years. And this chart shows the how its dissipation. So suppose the current carbon dioxide concentration is 100%. We are stopping everything. So the land, atmosphere, and all will uptake in the few upcoming years. This is the years from now. And even after 100 years, we will have depleted only or removed only by natural process, removed only 60% of it. So 40% of the carbon dioxide will still remain after 100 years. So even if we go, our children go, then still that carbon dioxide will be there. And you look, then the absorption of carbon dioxide by the ocean is a very slow process. You can see that here, even after 1,000 years, there is a range of uncertainty as well. Between 15 to 40% of the carbon dioxide still remains in the system, in the air, trapping that heat. So
that is very, very good at fixing CO2 and deplete different layer.
oh, it depends on, I mean, depends on what your purpose is. So if it is about again, regulating microclimate is good, but if so at a science level, you are working on a species which absorbs more and more carbon dioxide. Very good at photosynthesis. Yeah. If you can replicate it at a level over a large area, because see, that's why I said phytoplankton. They are important. They do that, and we have this natural natural primary productivity, which is absorbing all that carbon dioxide there. So,
But even for very- and that's something that many companies have been trying for ages to get it to be much more efficient. Yeah, but we don't having it, so far people have not succeeded. I mean, it's only been failed.
You can't just increase the levels of plankton in the ocean. You kill all
Guys,
the-
I think we should let the speaker go on.
Yeah.
I mean, there's only
Yeah.
15 minutes left.
15 minutes. Yeah. So anyway, I think I made the point. So even after 10,000 years, some close to 20% of that carbon dioxide will still remain. And where is all that heat being absorbed? This is a this shows a fraction of where the heat goes, and most of that heat, 93% to be exact, of that heat is absorbed by the ocean actually. And what we are actually feeling over here is rest of the maybe 7 or 3% or something, because land, ice, atmosphere, all of this together absorbs only 7% of the heat. So there is a lot of heat actually being absorbed by greenhouse gases. Most of it goes to the ocean. And the ocean, what is the average depth of the ocean? Anyone?
2 kilometers.
2 kilometers. Wild guess? Arnab? 1 kilometer. Sandhya? No, wild guess. I know I want wild guess. How much? 3.14. Ah, that's a good number. Yeah, average depth is around 4 kilometers. Okay, so you are the closest. Yeah. So you have to think that it's that depth of ocean over years, tens of thousands of years, that is slowly absorbing. Yeah, most absorption happens over the surface itself. Yeah, and I have put an analogy as well. It's each second that heat absorbed is equivalent to 6 Hiroshima atomic bomb. The energy from that atomic bomb. This is the additional heat absorbed by the ocean. Yeah.
Around 90.
Huh.
This is the Earth's energy budget. Yeah, so it's just industry going on.
Maybe, yeah. Anyway. So, and there also, even within the ocean, some oceans are warming much more faster. One of them is the Indian Ocean, where, which is surrounding India. And you can see temperature. So we talked about global temperatures going up to 1.1, 1.2 degrees Celsius. And if you look at our region, the Indian Ocean, there also temperatures are going up to 1.2 degrees Celsius and all. It's warming pretty much fast. And it's like basin-wide warming. And actually, if you, I don't know if I have figure, but though the northern hemisphere has warmed much, the Indian subcontinent hasn't actually warmed that much. The warming is actually around 0.6 to 0.7 degrees Celsius. So that changes the contrast that I talked about earlier, which makes the monsoon winds weaker actually. But again, there is more moisture also, right? So there is dynamics, thermodynamics working together. And the warming that I showed is just this. So this is based on all that ocean observations that we talked about for the Indian Ocean, and also model simulations. So so this is a comparison. The yellow or the orange is the observed changes in the ocean, and the black line is the model changes, and then it goes to the future scenarios. This is the, if we continue the business as usual kind of high emission scenario, this may not ever happen because nations haven't committed to reducing emissions. So we might be somewhere between blue and red. So which means that whatever we have seen until now is nothing compared to what is projected for the future. So projected is like 3.8 degrees Celsius per century. And that will have huge impacts because it changes the monsoon conditions and so on. Yeah, this is the picture. So this is a change in temperature during the 100+ years. You can see ocean is warmer, but land, especially some parts, northwest, is slightly cooler. This is the average temperatures again. doesn't contain the heat waves and all. Heat waves have been increasing actually over this season or this period. And you can see it changes the gradient. So this is a schematic of that gradient. So if this leads to a normal monsoon with warmer land during summer, now if the ocean is much more warmer than the land, the monsoon will weaken. So there is more rains, but more rains are happening over the ocean. So that is what is happening with the monsoon. And there is especially if you take some parts of North and Central India, you can see a monotonic decline in the monsoon rain. But at the same time, over the same region, extreme rains are increasing. So monsoon winds are weakened, but what is happening? There is more moisture. So there are episodes during that June, July, August, September, when the winds are slightly strong and it's bringing all that moisture in a short time and dumping over India. So you have long dry periods and spells of heavy rainfall happening. So you'll get a season's or a month's rain in a few hours to few days time. And that is what is happening here. And that's what, so you wish for, some water, it doesn't happen. And suddenly it all pours in and, creates damage. Changes in monsoon affects human health. Also, this is some of the research we have been doing recently. You can see a clear seasonal cycle. So this is for Pune, and we fortunately got some health data from Pune. And this is the case. The black is the dengue cases. The red is the dengue deaths. So this is all normalized, okay? Just to show the cycle. And this is the rainfall. So once you have the rains, there is a delay for the mosquitoes to breed, the virus for intrinsic incubation, extrinsic incubation before that, and you need the threshold of sufficient mosquito population, all those things. So if you understand this relationship, you can model and forecast. For example, if you have this much kind of rains, this time in Pune or Mumbai, in the next few weeks, you might have higher dengue cases or lower dengue cases. So we have used kind of AML methods to, understanding the data and then model it and make a forecasting system. And the same forecasting system can be used for future predictions also, because we have prepared the climatic projections for the future. We know tentatively how temperature, rainfall will change in future for Pune or Maharashtra. And we can predict how dengue cases might increase or decrease. So this can help in getting prepared, prepare policies, and so on. So this is just an example on how tightly linked monsoon and all are. You have 10 minutes or 5 minutes?
10 minutes.
5-10 minutes, yeah. So just I will talk about compound events. So we treat many of these weather conditions in separation, in isolation. But now many of these effects are overlapping. So recently, today Arnab told about seaface side getting flooded. That was some years back, but due to a high tide. But suppose you get a cyclone, strong cyclone on that coast, and bringing storm surge, huge waves. That's a lot of water. Sometimes they can bring in waves of high up 4 or 5 meters. So they bring in a lot of water. Now with climate change, the same cyclones are bringing in more rains also, because there is more moisture available. So it's raining more than earlier. And the sea level is also rising year by year, decade by decade. So if the same cyclone as 10 years back comes now, the flooding will be much more. And if you have high tide, like what you told, it will come into your labs, not just the sea phase. So that's the kind of compound events I'm talking about. Same with heat waves, droughts, and all working together like in a condition here, with the glaciers melting and no water. So you might have heard about Chiplun floods, which happened a couple of years back. So in Mahabaleshwar, like the hills over here, it rained up to, you can see in 2 days, 22 and 23rd July, 1000 millimeter. 1,000 millimeter is like even square meter, 1,000 liters of water, like that everywhere. So all that water gets down, and but the rivers are squeezed. It reaches Chiplun town. Urbanization is there. Doesn't have area for the water to spread out and get absorbed. It gets flooded. Not only that, it was coincided with a high tide and sea level rise over here. So the water didn't get flushed out. So these floods remain for a long time. So this is the kind of things for Mumbai also in the future. Mumbai may not get submerged, but it might get that floods might be much more stronger, intense, and may last longer because of these kind of compound events. Yeah. So I have marked the points: rains, river encroachment, sea level rise, high tide. These are factors which we can actually work on and reduce the impact. So we might, this is how rivers should meander. And this is true for Mithi River also. So if you look at Google Maps a few years back and see how the Mumbai airport was extended, you would see that that time the river was flowing in a perpendicular way actually. Rivers don't flow like that. So when heavy rains come, it will get flooded. So the Mumbai airport used to get flooded. So it's the same in this scenario. There is no space for water to spread out, even rejuvenate. So it carries on to the droughts as well, because groundwater doesn't get replenished. And these issues are solutions themselves, if you understand that. So there is no one-sided story. It's not just climate change, because if we talk just about climate change, we are forgetting directly with land use, land cover changes, river changes, biodiversity, human direct impacts. We are actually doing more harm, more impacts are coming than climate change actually. This is an example. This is the blue tarpaulin I was talking about earlier. So high rises, blue tarpaulins, and you can't even spot a river here. Oh, sorry. So this is the same river that I talked about. It's less than a canal now. And if all that water comes in and the sea level is also going up, storm surge happens, high tide happens, this water doesn't go out. So whether it will flood this area or a cyclone will, take away those tarpaulin roofs. So that is what we have to think about actually. This again from Mumbai, sea coming into the houses with a storm surge. And we have the data. This tide gauge measurement is actually from very close to here in Colaba. And this shows around in the recent period. So this is an earlier, long time, 3 millimeter per year, 5 millimeter per year. This from tide gauges from across the, so you can see how the sea level is measured using spot observations rather than just satellite. We have satellites also last 45 plus years. And what does this correspond to? What does 3 millimeter per year corresponds to? Per decade, it's 3 centimeter. Per century, it is 30 centimeter. So 50 centimeter for 5 millimeter per year, half a meter, right? Half a meter of sea level rise. What does it correspond to? How much land it takes? So let's see here. So if you know the slope of the coast and basic trigonometry, you can calculate how much of water get inundated. So if per decade, if it is 3 centimeter, around 17 meters of land can get inundated. Mumbai might be different because of the different topography. But for example, if you take East Coast, this could be a clear-cut scenario. So this is per decade.
Your previous.
Yeah.
In that you pull the down.
Yeah. Yeah. Good that you spotted it. So there are multiple things. Oh, okay. One major point. There are 3 ways in which the sea level rises. We think about, okay, the polar ice and all melting, right? And adding the volume. There is one more thing, thermal expansion of water. So all that ocean is getting heated up, 4 kilometers of ocean. It expands the volume of water. Okay, and this is uneven. Bay of Bengal is much more generally warmer. That is one thing. But the key thing is that the land over the North Bay of Bengal is subsiding also. When the Himalayas is going up, some part towards the eastern foothills, it's actually subsiding. The land is actually going down. These are geological changes happening over several thousands of years. So all this is adding up to that 5 millimeter per year. So the sea level rise is also uneven due to multiple factors like that. Yeah. So 17 meters. So we can calculate. We can project also in the future how much of land will be taken by the sea and extreme weather events. So suppose you have the monsoon time or the cyclone time, how much of water can intrude? And you can prepare your homes also, your infrastructure according to that. This is one of the first mammalian species to be extinct just because of climate change from our nearby region, Indian Ocean region, because of sea level rise and inundation. It was found in a small island near Papua New Guinea. It was totally wiped out. It was wiped out. And we can see signs of sea level rise even close in our own seas. This is one island, part of India itself. A satellite image earlier. Now, what are we doing? There are multiple ways to prepare our, whether it's home or even an island. So one way they are trying to restore this island, because this island is singing as well, is to, bring more grow seagrass as well as restore some coral reefs around it. Now, we do not know these are the best examples. We need many more these kind of experiments to see if these kind of islands and ecosystems can be preserved. So after this, they saw that a lot of biodiversity has increased over this region. The inundation has kind of reduced because these corals and seagrass protects these islands from getting inundated very often. Now, that's kind of multiple things that I talked about, from health to ecosystems to how the monsoon all working together and how it has changed over time, and how we can understand these changes for the future as well and get prepared. Thank you very much. Thanks a lot.
Thank you, Roxy. We're going to have a few questions.
Yeah, so regarding this reducing the carbon, a lot of companies are working on this direct carbon capture thing. Bill Gates has poured a huge amount of money. I saw in news. So what is the case in that? Like what they are actually trying to do?
So I would say so generally the consensus is that carbon capture should also go in parallel with other efforts, but the amount of carbon you can capture in the coming decades, it won't solve even a portion of the problem that we are facing. So even if you use the current facilities to capture the carbon, for example, 1 year, the amount of carbon you are captured from the atmosphere, you have to think it's okay. In the troposphere, it's like 12 to 18 kilometers, and it's well mixed gas, and you are trying to extract that. So the amount of capturing you do in a year may be equivalent to a minute or a couple of minutes of carbon you are emitting. And it's more, and you are spending more energy, electricity for capturing that. So it's actually a negative effect as of now.
One of the slides where you were showing the effect on health.
Health, yeah.
The rise of dengue cases, and then I think, was I mistaken that it seemed August onwards, the number of deaths were more than the number of cases by at least.
No, that is multiplied. The mortality deaths were multiplied by 20. So it's by 20, yeah. And though it is governed by seasonal cycle of rainfall, on long term, it is not actually rainfall changes. We see that it's the temperature changes that is expanding dengue. So in fact, globally, even malaria-prone regions are being overtaken by dengue cases because of increase in temperature and moisture also.
Yeah.
Hi.
Roxy, very nice. Thank you for coming over. This idea that you want to think about lifetimes of CO2 could be misleading, because you need CO2 at certain levels for everything to work around, because you would require that 250 ppm that you showed throughout the living history of people on Earth.
Yeah.
So what you need to sort of say is, what is the rate at which we are pumping right now, and what is the rate of compensation through other processes, which are still not good enough because there is accumulation.
Yeah, exactly.
So if those rates are understood, that would be a better way to project this question.
Yeah. So it's all about the balance.
It's a little bit putting fear in people's mind that this much emission, so it takes 100 years to get it to 40%. But those things have to be weighted out with respect to how much you are burying in the CO2 by natural other processes.
Yeah, so that average 15 degrees Celsius that we talked about, global mean temperatures, which was originally due to the natural, that's that balanced temperature, because there's a balance of the heat energy budget that the Earth receives. Okay, this much comes in, this much goes out. Same way with the carbon dioxide as well. Yeah. And it's because of that carbon dioxide or the greenhouse gases that's already present that we have a temperature of 15 degrees Celsius, which is optimal for us. Otherwise, we would have been minus 15 degrees Celsius. But now we are pumping in additional carbon dioxide, which is actually taken this out of balance. Definitely. And it's about that additional carbon dioxide, additional heat, and additional imbalance in the Earth system that we have been talking about. Definitely.
There are different meteorological effects, which are happening due to climate change.
Yeah.
And you have different levels of confidence as to how much is actually due to climate change or not. Now, in this, I think you have far more confidence in terms of the amount of rainfall being correlated with overall temperature increase or carbon dioxide increase. But what about the frequency or the intensity of cyclonic storms? Cyclonic storms affect our coastal regions very strong.
Yeah.
And until a few years ago, there was some debate as to whether really climate change, how confident you are about category 4 and above cyclones. Has that situation changed?
Yeah, so this has definitely changed for the Arabian Sea. So for the rest of the ocean basins, there was no clear indication. So generally cyclones form over warm waters of the ocean, which is why we call it tropical cyclones. Generally you need ocean surface temperatures about 28 degrees Celsius. And it should be that, because that will give consistent supply of heat and moisture for the cyclones to develop. And what is happening is that, so this Bay of Bengal, Arabian Sea, part of Arabian Sea is part of a warm pool where temperatures are generally about 28 degrees Celsius. Now this is expanding. So Arabian Sea, if we take the entire Arabian Sea, including the west and south part of Arabian Sea, average temperatures used to be 26 degrees Celsius. Now average temperatures are around 28 degrees Celsius. So it is supporting more cyclone and more intense cyclones. And we see that from the data. So in the last 40 years, where we have clear data of both ocean temperatures, cyclones as well, and we have better models. So what we have seen is that there is a 50% increase in the number of Arabian Sea cyclones. So earlier in the, for example, 1980 to 2000, for example, we had one cyclone in 2 years in the Arabian Sea, roughly. Now we have one cyclone every year, roughly, on an average. So this is, and not only that, there is something called rapid intensification. These cyclones are intensifying fast because there is a strong supply of moisture and heat. So they are intensifying from a category 1 cyclone, which is like 100 kilometers per hour, to a category 4 cyclone, which is like 200 kilometers per hour speed. You can imagine the car speed and all. And that is happening overnight. So within maybe 10 hours. And our models, forecast models are also unable to pick it up. For example, cyclone Tote, which the West Coast, or cyclone Nargis. So all these intensified rapidly, sometimes in a 6 hours time or 12 hours or 20 hours. And our model forecasts are unable to pick this kind of rapid intensification. They are able to pick up cyclone forecasts have improved a lot from Odisha cyclone time. They are able to forecast, okay, this location it will come, it will be roughly this intensity and all you need to work with. That is coming out right. But this short-time intensification, even models are unable to pick up. So this is happening, and we have clear data to show that. And that is worry for the West Coast. Yeah.
Yeah, thanks. Hi, nice talk. I had a question on the projection curves that you showed in the end. 3 curves. One of them just diverges upwards, but the other 2 seem to saturate. Can you elaborate on what sets in the saturation over what time scales?
What? Once again, what?
If you look at the 3 curves, 2 of them are those who start saturating after a certain number of years. What factors kick in this saturation? The blue and the green.
So this is based on the shared socio-economic pathways that countries will take, not just based on, so it based on development as well as the commitments they have taken up, which means that maybe by 2050, some of them are committed to reduce emissions or energy efficient pathways. So some of them you will see it will be flattening for at some point. So it will not go down drastically because of the same thing, like carbon dioxide will still be there, but it can flatten. But this is almost impossible. If we want this, we actually needs to work on extracting all that carbon back. Yeah. And with things like war and all is also put into this regional rivalry, it is called. So one of the scenarios is regional rivalry, where climate commitments take a backseat. Yeah.
Thank you.
Yeah. You mentioned subsiding of land, one of the factors that affects the rising of sea level.
Yeah.
Of course, that I guess is humanly impossible to control.
No. Yeah.
How widespread is this? What fraction of sea coast in the world would be affected by subsiding of lands next century?
This is, I mean, I do not have much idea about rest of the world, but I know that the Bangladesh coast, the subsidence is under detectable levels, which adds up to the sea level rise. That is one thing why there would be mass migration from Bangladesh to rest of the regions. So this is in a worrisome level, and they have high cholera cases also. And this also have a connection with the sea, because the cholera bacteria, it attaches to the zooplankton in the sea. So when there is sea intrusion, it comes into the drainage system, into the pipelines, and because the hygiene in some areas may not be that great, it gets into the water distribution system also, and people get cholera. So there are multiple issues coming up with this subsidence and other things culminating into that sea level rise over that area. But other regions, I do not know how much of a it has not come to a big notice for me.
Some of this reclaiming of land using, like seeding more coral leaves or plants.
May not be priority. Even we are not doing much. Whatever I showed was experimental basis actually. It won't actually help us in adaptation. I mean, we are not doing in such a large level where we are adapting to these changes. Otherwise, even our coastal expressways, we will build based on how it is going to change in the future. And some of the expressways, even through passing through Maharashtra, they are causing floods because they are not allowing water to pass through. So
Yeah, okay, question there. So
GC has been making these reports now for the last, 30, 40 years. And projecting these various different scenarios. So over the last 40 years or so, where do we stand today on those curves? Because these projections have been coming for, so are we somewhere in between? Are we on towards the top today? Where are we?
Yeah. So actually, with each IPCC report, we are actually seeing that we have actually underestimated.
Yeah.
Because better measurements are coming, models are, so many times scientists try to be less alarmist. And, we are scared about projecting these numbers. And we are at the conservative side, actually. But data is actually pushing that curves up.
Further and further into red.
So we are reaching actually that 1.5 the current IPCC says that we will reach. So earlier it was like, okay, we should stop by 1.5 and all. Now we don't actually have hope, though we say in public, okay, we should stop at 1.5. But what IPCC report, if you look at that, the data says is that between 2020 is already over, between 2020 and 2040, we will hit 1.5. So we are going through that 1.5, just that we will get that average by maybe 2030 or 2040 only. And 2 degrees Celsius between 2040 and 2060. That is by, I'll take 2050. And 2050 is when we all will be at our 80s, maybe. And we will be facing the brunt of it. So it's not like, our kids, just our kids. We ourselves will be facing the brunt of all that climate change in our lifetime.
Thank you.
yeah, so I'm not giving was the last question. So you give me to.
Yeah, so should we believe that BBC report that says Mumbai is going under?
No, by 2050, no, Mumbai is not going under. But prolonged floods, what is important. Prolonged floods, yeah.
Okay, let's thank Roxy again. Please join us for tea. They're waiting for us.
You're going back to Pune today?
Yeah.
But I'll email you.
Please.